Hey everyone, welcome to The Explainer. Today, we're unpacking a really wild paradox in the world of environmental science. We're going to track the journey of a highly toxic chemical, a substance that is literally plastered with severe warning labels, that ironically serves as the exact tool we rely on to keep our drinking water clean and safe. It's this incredibly delicate high-stakes balancing act of chemistry and biology, and the way we manage it impacts literally every drop of water that flows out of our taps. We've got a lot of ground to cover today. First, we'll meet copper sulfate. Second, we'll look at the algae bloom threat. Third, diagnosing the water. Fourth, calculating the right dose. Fifth, the ecological aftermath. And finally, smarter lake management. All right, let's dive into Section 1. Meet copper sulfate, the environmental hazard. If you pull up the official safety data sheet for copper sulfate, the very first thing that hits you is this stark, massive skull and crossbones. It's intense. The warnings are practically screaming at you. It's toxic if swallowed, it causes serious eye irritation, and it can severely damage your skin. Basically, it is not something you want anywhere near a living organism.
But here's where it gets really interesting. Take a look at the environmental warning. It explicitly flags chronic aquatic toxicity. That means it is highly toxic to aquatic life, and it has long-lasting adverse effects.
Just to hammer this point home, the datasheet gives a completely unequivocal directive. It literally reads, "Do not let product enter drains, streams, or other bodies of water. Discharge into the environment must be avoided. Under no circumstances should this stuff go into a lake." And yet, municipal water managers actively and purposefully dump thousands of pounds of it into our drinking water reservoirs every single year. Sounds crazy, right? Well, to understand this paradox, we have to meet the enemy they're actually fighting.
Which brings us to Section 2, the algae bloom threat.
You know that thick neon green scum you sometimes see floating on the surface of a lake? Yeah, that is not just an eyesore. It's a massive ecological disaster in the making. That's a severe blue-green algae bloom. When this algae gets fed too many nutrients, it just hyper-proliferates. It multiplies completely out of control and completely wrecks the water's natural balance. And let me tell you, the fallout from these blooms is an absolute nightmare for the folks managing our municipal water supplies. First off, some of these algae produce toxic scums that are legitimately lethal to fish and local wildlife. They can even give humans nasty skin rashes and gastrointestinal distress. But even beyond the direct health risks, they just wreak havoc on infrastructure. They give our drinking water this awful, swampy taste and smell, and they physically clog up the massive filters at water treatment plants. That drives operational costs through the roof. It's a full-blown crisis that demands an immediate intervention.
So moving on to Section 3, diagnosing the water.
Now, lake managers can't just go throwing chemicals around blindly. They have to act kind of like a doctor diagnosing a patient. But how do you actually know the algae is taking over before it turns into a giant, visible green sludge monster? Well, the secret lies in the invisible chemical changes happening right beneath the surface. When a bloom is kicking off, these hyper-photosynthesizing algae are pumping out so much oxygen that the water actually exceeds its maximum natural capacity. Take a look at the threshold for 25 degrees Celsius. If the water is holding more than 8.2 milligrams per liter of oxygen, it hits what we call supersaturation. That right there is a massive red flag that an invisible algae explosion is already underway.
So managers run through a diagnostic checklist. They're looking for decreased transparency, that infamous pea soup color, and of course that oxygen supersaturation. But crucially, because the algae are aggressively sucking carbon dioxide right out of the water, the fundamental chemistry shifts. This causes the pH levels to spike above 8 units, and the alkalinity to just plummet. When all those indicators line up, yeah, the diagnosis is confirmed. You've got a severe algal bloom.
Section 4. Calculating the right dose. 5.4 pounds. Seriously? According to extensive research, a mere 5.4 pounds of copper sulfate per acre of lake surface is entirely sufficient to control these problem-causing blue-green algae. But here is the absolute wildest part. In practice, some lakes are getting wildly overtreated. We're talking operators indiscriminately dumping up to 80 pounds per acre. That massive over-application is exactly what leads to toxic sediment buildup and dead fish. So precision, it's absolutely everything. And the math behind this precision makes total sense when you think about the water column. You don't actually need to treat the entire volume of the lake all the way down to the bottom. Blue-green algae contain these tiny little gas pockets that make them float. Therefore, the vast majority of the algae exist right at the surface. By calculating that 5.4 pounds specifically for only the top 2 feet of the water column, managers can effectively knock out the threat while drastically reducing the total amount of toxic chemical they're putting into the environment. But there's a chemical catch. Remember how the algae bloom itself causes the lake's pH to spike? Well, in high pH water, copper sulfate quickly precipitates. It basically turns into a solid and sinks right to the bottom, making it totally useless against floating algae. To outsmart this, scientists mix the copper sulfate with citric acid in a 2-to-1 ratio. The citric acid acts as a chelating agent. It's a real game changer because it keeps the copper dissolved in the water way longer, maximizing its algae-killing power right where it's actually needed. Which leads us to Section 5, the ecological aftermath. Let's trace a real-world 10-day timeline observed by the Illinois State Water Survey at Lake Lonomi. Okay, day 0. The copper and citric acid go in. Over the next 3 days, hey, it works. The algae density drops. But because millions of dead algae cells are now decaying, bacteria start eating up all the oxygen in the water. By day 5, the dissolved oxygen hits rock bottom. And then here comes the ultimate plot twist. By day 7 to 10, a massive algal rebound happens. It's often worse than before. You can really see the roller coaster here. Notice how violently the dissolved oxygen drops in those bottom metrics from day 0 to day 5 as that dead algae decomposes. That extreme oxygen drop severely stresses out the fish and any bottom-dwelling organisms. So we've temporarily killed the algae, sure, but we've traumatized the entire ecosystem in the process, basically setting out a welcome mat for the algae to just bounce right back. Let's wrap things up with Section 6, Smarter Lake Management. The research on this is crystal clear. Just listen to this quote from the Illinois State Water Survey. They point out that this rapid rebound effect, quote, demonstrates the impossibility of completely eliminating algae and the futility of using copper sulfate to prevent algal blooms. In other words, routine preventative dumping of copper sulfate is ecologically irresponsible and honestly just completely futile. You literally cannot poison your way to a perfectly balanced ecosystem. So instead of just treating the symptom with harsh chemicals, holistic management actually goes after the root causes. If your water tastes bad because it's being pulled from the oxygen-starved bottom of the lake, just move the intake pipe closer to the surface. Managers can also install mechanical aeration systems to keep oxygen levels up. They can optimize the physical filters at the plant, and perhaps most importantly, they can stop fertilizers and excess phosphorus from washing into the lake in the first place. And that brings us to the ultimate takeaway for this explainer. Copper sulfate is an incredibly powerful, highly toxic tool. And yes, when it's calculated with absolute precision, it can save a water system from an immediate, severe algae crisis. But as we've seen today, it's a major double-edged sword that completely disrupts the delicate balance of aquatic life. Which really leaves us with one big question to ponder as we think about the future of protecting our environmental resources. Is the best chemical treatment actually no chemical at all? Thanks so much for hanging out and exploring this with me today, and keep asking questions about what goes into the water we drink.